Welcome everybody to the last final lecture. Thanks for joining me today. Um, so, uh, okay. So today we're going to continue with the strong regularity, and here is more exercises about this. Um, so if R is show that if R is strongly regular, then every localization is also strongly regular. For every prime. And we're going to define a non-local ring is, or a ring in general, I guess. A ring in general is strongly regular if its localization are strongly regular. Okay, and now in our new setting, R is going to be a domain, finite domain. So we're going to forget about the local property for a moment. Okay. I'm talking a lot about some regularity. Let me just recall this as a parenthesis because I know we saw that just yesterday. And this can be the definition now that we're assuming domain. And this is consistent with everything else has been done. So R is strongly regular. If for every C inside R not zero, there exists an E and phi from R1 over P to the E to R, such that P of C1 over P to the E equals 1. Here. So, theorem. This is by Hobson and Hineke. That says following: let X be a non-zero element here, be such that R localized at X is strongly regular, and there exists an L such that phi of R1 over P to the E to the S, sorry, to R is such that P of X1 over P to the L goes to 1, then R is strongly regular. Okay. So this is a criterion. Yeah.
Sorry, what were you defining back in that first definition?
This one is strongly regular ring for rings that are not local. Because so it's the same definition as before.
Right.
But that's not. It's more reducing to the local case. Yeah. So something is strongly regular, but its localization are strongly regular. Pretty much how we do Cohen-Macaulay. Yeah? So, and then now that we're restricting ourselves to domains, everything is with exactly the same definition that we had before. But here I'm trying to deal with the non-local case. Yes?
So, because Frobenius is still fine in the non-local case, right?
Is it, pardon?
Frobenius is still You can still define a map in the non-local.
Yes, of course, yeah.
So why do we define it that way?
Oh, well, the issue is that I wanted to, so the issue that I didn't find it first in the local case and then in the non-local case is because I don't want to deal with minimal primes. So the definition official, like the pushing the papers, is that C outside every minimal prime. So I just wanted C different than 0 because that makes life a bit easier. But if you're in a domain, it's just equivalent. If you're in the local case, one has to do some work and it's equivalent for strongly regular. But then today we're going to work only with non-local domains. That's why I wanted to do that precise thing in this case. Makes sense?
At least you may have said this before, but so for every C there's an E. So it's not like every E is like
Yeah. This exists because let me just it's here too. There is one.
There's one, but is it the case that big enough could work or things like that? E big enough?
Yeah, I mean that's if you ring strongly regular, then E big enough is gonna work. But yeah. We good? So let's prove this. So let's take a C inside R, different than 0. Then there exists an E and a phi from R1 over P to the E to R. So localize here. I'm taking an element here, but this is contained in R localized at X minus 0 now. Because remember, we're assuming that that is a domain. But this is a true containment. Okay, so because it's different than 0, I'm using the fact that R localized at X is strongly regular, so we can find something that sends a root of this to 1. What? But this is in R localized at X. Okay, but now, because the ring is a finite, so this, what this element is? So phi inside from R localized at X, R localized at X 1 over P to the E, R. And we know that this is the same as from R localized at X, 1 over P to the E, R, all of these localized at X. Because everything involved here is finite generated, no? Or assuming finite. So the fact that we have this element here means that we can lift it to something here. So take one of those liftings. So there exists a phi tilde on R1 over P to A to R, such that P tilde of C1 over P to A, this may not go to 1 because we have to pay the price of lifting. So this is going to be equal to X to some power. That's the price that we pay. But then, since, remember the splitting prime, probably this is for the local case, but let me see. Since how do I do this? So since, let me see. Sorry, I did the proof of local. Okay, since X is outside P, the splitting prime at every localization, then any power, outside is outside of every splitting prime of any localization for any maximal ideal. And then here, thing that I will ask you some sort of to believe me is that this implies, because this notion is kind of local, this implies that there exists another splitting, let me see, gamma from R1 over P to the E to the, no, sorry, to the T, right? Such that gamma of X to the A over P to the T is equal to 1. Let me call it this difference just to not mess up my notes. Theta. Okay. So what we're gonna do is let phi double tilde, I guess, from R1 over P to the E plus T to R1 over P to the T. So we're gonna take the P to the T root of this map. We have done this several times, so we're going to do an element here that goes 1R over P to the E plus T is going to go to P tilde of R, 1 over P to the E, and then to all this, we're going to take the T root. And this map is R1 over P to the T linear. Are we good so far? What X for me? Oh yeah, because there is a split, that sends this one to 1. And then once you localize this map, the localization of this map, or the inducing in the localization, is going to send this element still to 1. So that means that it's going to be outside I sub E in any maxima like that. And that's enough to be outside the splitting prime, which is the intersection of all the I sub E. Make sense? Okay. Good. So these are linear. So we're going to set gamma equal to theta, the one that we have over there, composed with bar phi double tilde, and then what this element does, what this map does. So if we evaluate that in C, we evaluate that gamma in C 1 over P to the E plus T. This is going to be equal to theta of bar phi double tilde of C 1 over P to the E plus T, which is equal to theta of P tilde of C 1 over P to the E, all of this 1 over P to the T, which is equal to theta of 1, theta of 1 over P to the E, sorry, no, X to the A, 1 over P to the T, which is the same as theta, X to the A over P to the T, which by how we construct theta is equal to 1. And this is how we satisfy that definition. And something, this is useful because they give us a criterion of regularity. But something that this theorem is kind of screaming at us is the non-strongly regular locus is closed. This is closed, no? Because here what we're saying is the localization being strongly regular is telling us that at least in the open statistically open set given by X, that's in the strongly regular locus, no? So that's open. And then I'm saying, okay, if that were closed, that means that this has two options. Either it is in the locus, the non-locus, or it's not. And this is telling us, oh well, it's not. So the closed part is also not there. Now this is just like one thing that I'm not. I know that what I'm saying is not totally precise, but this can be this is kind of the intuition of how you can use this theorem to prove the following. Is Zariski open. And for those who are familiar with tight closure, this is gonna be just the Zariski closure. So this is the complement given by the big test idea. Oh yeah, because well, it depends. In any, because we're assuming domain and then a finite. So these every regular ring is extremely regular. So this contains the regular locus. So if the regular locus is not empty, which happens in every reasonable ring, then this is not empty. Okay. Okay, and let me just do another exercise. This is show that if R is strongly regular, then but when you add a variable, a polynomial is a variable, and the power series, then these two are also strongly regular. Question to think about. So let's suppose that M is local. Suppose that R is local. And X is a non-zero divisor, such that R over X is strongly regular. Is R also strongly regular? So the question is, does strong regularity deforms? Yeah, people who know the answer in the answer, don't tell to the people that don't know the answer, because this is fun. This is fun to think about. Well, not today, maybe tomorrow. During the trip, you can discuss the solution. Follow me? Sorry, I cannot.
Is the converse true? The converse
No, it's false. The comment is false. Yeah, we don't take a false in the ring and take the equation of something that is not properly x to the 2, or xy, which is not a domain. Yeah, no, this is the thing about deformation. No? One spell deformation is you talk with a hypersurface. The hypersurface cannot be better than the original. That's kind of the theory, well, the idea behind some deformation theory. But well, it is out that purity does not deform. So this idea of meta theorem does not always work. No? And we don't know about the injectivity, which is another problem we discussed. Okay, so now we're going to move to a very specific kind of rings. We're going to talk about determinantal rings. So Spoiler alert, well, we're going to prove that these are strongly regular, but more than that. So, sorry again, we're going to change the setting, and I wish I could say this is the last time I change the setting, but it's not, so I'm sorry. So K is an finite field. X is going to be a matrix of variables. It's a matrix of variables. R times S, M times this matrix of variables with R is smaller or equal than S. We're going to take S to be the polynomial ring in this with the variables from the matrix. We're going to take I, because it's going to be equal to I sub t of X. So this is the t by t minus of this matrix. And we're assuming that t is smaller or equal than R. And then we're going to take R equals to S over I. Okay. So let's do, this is a really fun exercise. To show that t plus a of x, so the t plus a by t plus a minors of these ones are contained in the I t plus x a minus 1 symbolic power. This is a very fun exercise. If you do, let's just do the 3 by 3, just for it. So we have here A, B, C, D, E, F, G, H, I, J. Oh, this reminds me of my daughter. Yeah, that's the favorite song right now. Okay, so you take this determinant. What happens when you take remember the determinant? Symbolic powers can be defined in terms of differential operators, no? We saw that. So for instance, the second symbolic power, let's take f equals to this determinant. And we're going to see that this is inside here. This is my matrix X here. This is a special case of this exercise. If we take the derivative in respect to A of the determinant, anything that doesn't have A is going to vanish, no? So the thing that you take with B times this part is going to vanish. The C with respect to this part is going to vanish. So the only ones that are going to successfully survive is this times this minus this times this, which is up by 2 by 2 minus, no? And then this A has nothing special. It's just a variable. You can take a permutation and you see that things is going to work as you expect them to work. It's not the proof, but it's like the key idea behind this proof. Or the initial idea behind this proof. Yes? Sorry, here T is 2 and A is 1. Oh, no. A is 1. And then it was A plus 1. It's plus 1, sorry. Thank you, Lisa. You got my time. Oh, they haven't worked my notes. I just sometimes get too excited and forget to look at them. Thank you, Lisa. Yeah. T is 2, A is 1, and then this is A plus 1. Thank you. I mean, that is also true, but it's not as interesting. Okay. Okay, so now, another exercise is the height of this one, this ideal of I, or the t by t minus, is S minus t plus 1 times R minus t plus 1. And there is a fun interpretation of this. If you look at this, you look at the solid T by T boxes. So what I mean is, if you minor, this is 2, look at those minors that are all together, that you don't have to cut. For instance, in this one, I think of this as a solid 2 by 2 box, or this one, a 2 by 2 box. But if you take the minor given by this, that's not solid. Make sense? This is the number of solid 2 by 2 boxes.
You were just outlining for the first example? The argument you were outlining in the first example, is that okay even though we're in favor?
Oh, no. That's what it says, that's the initial idea. So that's not a proof in general. I mean, we'll give you a proof in characteristic 0. And yeah. Yeah, that's what, I'm not claiming this is a proof. No, this is an idea to start working with the proof. Yeah. Okay, so let's do, this is not setting, this is more like a notation. So let's pick A and B inside 1 until R, and C and D inside 1 S, with A is minor or equal than B, and C is minor or equal than D. So we said we're going to take a submatrix from A, B, C, D. This is going to be as the matrix, the submatrix of X with rows A plus 1 until B, and columns C plus 1 until D. Okay? So taking the submatrix that has pretty much this interval of rows and this interval of columns. Okay? And now we're going to define a polynomial that's going to look very crazy in definition. We want to see it in a picture. It will make sense. Okay, so let me do 6, 1, 2, 3, 5, 1, 2, 3, 4, 5. Okay, so this here I'm thinking in a 5 by 6 matrix. Every dot represents a variable. Okay, let me just put on a bunch of colors for this. Okay, so first we're going to take F is going to be equal to the product of L equals 1 to T to R minus 1. And before I write this, that is going to be confusing for me. So let's set T equals to 3. For me? Open?
Too many columns.
Oh, yeah. No. That's easier to fix than adding dots. Well, it's quicker. Okay. So T is equal to 3. So I'm going to paint in blue this, 2, 3. And what I mean by this, I'm coloring the elements that are in the diagonal of this matrix. No, this diagonal defines a submatrix, no? Like this one. It's like the one that contains, I'm not really, no. So this is one of the reasons I do algebra, to avoid drawing too much, but then they are useful still. Anyway, so this 3 by 3 matrix. And then, I'm coloring the subdiagonal to refer to that matrix. Okay? So, I want to take the product of the determinant of this matrix and the one that's given by this. Okay? I go except to the maximum minor. I want to go from those here in this corner that have size t plus 1, but go all the way except to the maximal minor. Those shifts at maximal minor. Okay, so to write that, then I go from things that have size t until r minus 1, and then that of x 1l. So we go to these columns, and then r minus l plus 1 comma r, this one. And then I want to do, so I should write this with blue. I'm just going to write the parentheses with blue to see which ones are required. Now, let's do with the maximal minors. So this. There are 2 maximal minors here in solid boxes. Okay. So I'm going to go now with the maximal minors in red. So what I do is this is the product from L equals to 1. I forgot the other one, which is going to be S minus t plus 1 minus 1. Let's see it more correct. Minus 1. For that of x, 1r, and then l plus r minus 1. Okay. So we're going to take the maximal minors that give solid boxes. Okay. And then finally, we're going to do the same thing that we did with the blue, but with the opposite corner. So we take this. And product L equals 1t to r minus 1, that of x 1l to s minus l plus 1 s. And as you can see, I'm struggling to write this and to even color this. So this didn't occur to me. No? I learned this polynomial from a paper of Lisa Sesha, who's here, to study Knudsen ideas. So the one that she was working is this one, but taking t always equal to 1. And then in the work that I'm going to talk about soon, what we did is just code it a little by t. Okay, so why do I want this polynomial? Well, something that we're going to see is the following lemma. If h is the height of the ideal of 2 by 2 minors, then this polynomial is set in the h symbolic power of the minors. And if you did the problem set from Tuesday or Wednesday, I don't remember, these start smelling as if purity. So this is going to be related to that there. So let's work with this. So let's prove it. So that of x 1l r minus l plus 1 comma r. So these are the blue ones. This one is going to be inside I sub l of x, which is contained in r minus t plus 1. So this one is in the symbolic power 1, which is the same as the ordinary power 1. Then this is going to be in the symbolic power 2. And then that of the maximal minors, we have 1 over L S minus L plus 1 comma S. This is inside in I sub R because it's a maximal minor, and this is contained in I to the R minus T plus 1. And then the green ones is pretty much the same as happening here with the blue. Yeah. Yes.
Sorry if I missed it, if you said it already. Does F have a name?
No. As far as I don't know. It has a name, you said? No. As far as I know. Okay. And then we have that x1l s minus l plus 1 comma s inside in I sub l of x, which is contained in I symbolic l minus t plus 1. Okay. Okay, so what happens? F is going to be, well, in the product of all these, in the product of all these, and product of all those, which is from L equals to T to R minus 1, I L minus T plus 1. This is counting, multiplying all the ones here that appear. But it happens twice, so I'm just going to do it square. And then in I, R minus T plus 1. This one, but then this happens as many maximal minors you have. Solid maximal minors, so it's going to happen to the S minus R plus 1. I'm going to do it this way because it's not a symbolic power, it's just an ordinary power. But all of this is contained in, because symbolic powers behave well, no. The symbolic power A times the symbolic power B is contained in the symbolic power A plus B. May not be equal, but they are contained. So if you add this many times and then multiply by 2, what you get is R minus T plus 1, symbolic, and this one, well, this is easy, is R minus T, R minus T plus 1 times S minus R plus 1. And then if you do the sum, this is contained in I S minus T plus 1 times R minus T plus 1, which, not surprised, is the height. Okay?
Please.
Yes.
So in the second factor is S minus R plus 1 there.
Yes.
The red factor.
In the red factor. This one or this one?
Yeah, in the product.
In the product.
Yeah. S minus R plus 1.
Minus R. Oh, of course, yeah. Thank you, Jan. Thank you.
Plus 1.
Plus 1. Yeah. Thank you. Thank you, Jan. Yeah. Yeah, right. Yeah, that's why this cannot be a yeah. Yeah. Okay, thank you. Yes? Oh. There was a question? Oh, hold on. Sorry. We good? Okay. Go.
So, this polynomial, does this have does what it cuts out have any meaning, or is it coming from like some combinatorial argument? Motivation.
Well,
The way you presented it makes me think of like something with the programs.
oh, well, yeah, I mean, it's gonna come from,
Is there some interpretation?
What period? This is the person right to answer that, but, I mean, it comes from one answer? So, what do you think? You want to say it just louder? No words. It's just like, it comes from, I mean, it's related to Brown devices, because the way she found it, correct me if I'm saying something wrong, is that, it's the Knudsen ideal. Knudsen ideal is something characteristic-free, that you have a polynomial and then you look at the Knudsen family of that, and then that family is going to have very nice properties with respect to the Gromner basis. And then it turns out that every Knudsen ideal prime characteristic ends up being pure. And that is like a very nice relation. For instance, on the Knudsen ideal, once you pick initial ideal, all of those are going to have a square free Gromner basis, a square free initial ideal. Did I say it was right? Okay, thanks.
So let's give the proof, the three matrices you are taking determinants of, the last two are equal, so I don't think, maybe should.
The last two matrices are equal?
So maybe you want to change the middle one.
These ones? These two?
The bottom one in the first column and the top one in the last.
No, sorry.
You read the green one twice.
This is the same.
You wrote the green one twice.
Yes.
Esta de aquí arriba y esta
y
de
esta.
aquí abajo son iguales.
¿Cómo así? Okay. Gracias. Sorry. I should have more on my notes. I'm sorry. Thank you, Manu. Thank you. It's L, L plus R minus 1. Yeah, thank you.
Okay, and also I cannot read the last exponent in the right, the top is the right. No? The last two pages. What is that? No. Okay, yeah. Okay.
Yeah. So, and today I didn't bring coffee, so I cannot correct that. Okay. Sorry. Okay, we're good. Okay. So, okay, I'm gonna use this. Pretty much, I mean, I did a spoiler. No, this we're gonna use this polynomial to show that the determinantal ring is strongly regular. Sorry. Oh, I spoiled my spoiler. Okay. It's a pure, but we're gonna prove that it's actually strongly regular. And this is why we need to start at t and not from 1. From theorem. This is due to Hoxton and Hünecke. But what we're going to do is a different proof. The way they did now. They did a different proof. They didn't build any of these polynomials. So, classic theorem with a new proof. So R is an strongly regular ring. So proof. So we proceed by induction on t. So for t equals 1, we're done because the 1 by 1 minus of x is just the maximal homogeneous ideal, no? R modulo the maximal homogeneous ideal is a field, which is it's not regular. It's regular. So let's do q minus 1 implies 2. Okay. And then from we're gonna take this p from s 1 over p to s. This is gonna be the trace map that you learned in your worksheet of Fedder's criteria. So be the map from the worksheet. So we know that every map that goes from R1 over P to R comes from pre-multiplying this by some polynomial, no? Or the root of some polynomial. Okay, now since F is inside in I symbolic to the H, then we have that F is inside I symbolic H times P minus 1. Because, sorry, this one to the P minus 1. And then I'm gonna keep this here. And this is where the combinatorics and the really cool thing about happens here. So let this be the diagonal X order. So what I'm saying is this variable is bigger than this, and we go this way, and then the next one is this one, and then we go this way, and then just we go from right to left. Well, here is from left to right, and from top to bottom. Okay. So x11 is bigger than x1s, bigger than x21, and so on. So let's see, what is going to be the initial term of this first blue minor? So the first variable, the biggest variable is this one, and then among the ones that have this one, in this 4, the biggest variable is this one, and then this one. So the minor of this, its initial term is going to be the blue dots in the diagonal, or the next one is going to be the blue dots in the diagonal, and so on. So the initial term of F is going to be the blue, red, and green variables, no? Which is square free. So if I do this to the P minus 1, initial order of P1 with multiplication is this going to be BRG to the P minus 1. Is it making sense? Which, by the way, is outside M bracket P to the A. Sorry, P. Now, I want to modify this a bit more to play a bit more. So what we're gonna do is we're gonna type y is gonna be the multiplication of all the variables over the initial term of f times xr, 1. So here we're taking all the white variables except this one. Okay? So I'm gonna give that a different color. This one is gonna be orange. Okay? So I'm gonna take G to be equal y times f to the P minus 1. So the initial ideal of G is equal to the product of all the variables to the P minus 1 to all the variables except in that corner, which is outside in M bracket P, and therefore G is outside M bracket P, and because symbolic powers are ideals, G is also inside I symbolic H P minus 1. So we already know that this is contained in I bracket P 2 dots I. So we just proved that the determinant ring is set pure. Only that. But we want more. Well, we're not satisfied with just purity. We want what we say the whole enchilada. So we're going to take P bar phi equals to capital Phi G 1 over P. This map. We know that this is going to give us the splitting, no, from Flanders criterion, the work that you already did yesterday. And something that I'm just going to say we know that. I'm not going to prove it because it's just some computations. But yeah, my time is fire. So these one sends R1, but pretty much by construction, to 1. This variable pretty much by construction splits up. So now, in order to finish the proof, we need to see that the localization of that element is strongly regular, no? So we have for matrix X, no? And in S, localized at X R1. Once we localize at this one, or matrix, this one, we can apply row and column operations, no? The matrix. And because this is now a unit. So we can divide by that unit and get a 1. And with this one, as we did in linear algebra 1, we can erase the full column, what it is, and the full row. So this matrix is going to be equivalent, yeah, to something that has a shape like this. And here you have y, 2 times r minus 1, 2, y, r minus 1, s. And this y is just like, oops, oh, sorry. So this is equivalent. These y's are some combination of the s is built from the x by the row column operation, which is like divided by this variable and then adding the things properly. Oh, sorry.
Is that P at the beginning of the proof the same as the P at the end? Math.
No.
Or the bar P?
No, sorry.
That's different. Okay.
Yeah, this is with the map from the worksheet. No, this is this is the same. Sorry.
Oh, okay, yeah.
Yeah, thanks.
Great, thank you.
Yeah. Thanks. Okay. So this is equivalent to this one in here. And then we can see that the t by t minors, once we extend, correspond to t minus 1 by t minus 1 minus of this one. So then R localized at X R1 is going to be isomorphic to a polynomial in kind of the variables that we lost. So X R1 until X R S, X 1 1, X R minus 1. So the variables that were displaced by this one, and then we'll have to add the X R minus 1, 1, R1, X, also R1 minus 1, and then the variable. Ooh, okay, I think we can. I hope I don't need this later. And then this one with the matrix Y, and then the t minus 1 minus the Y. And then we're done with the proof because this one, by induction, is strongly regular. We had some variables, is strongly regular. We localize, it's still strongly regular. So this whole thing is strongly regular, so this one's strongly regular. And then the inner ring is strongly regular. Corollary, the determinant ideas are Cohen-Macaulay, which was known before, no? Now we know more things about that. Okay. So, I need to go to a detour and then do another setting. Sorry. Because I wanna push this idea. Because this new proof is gonna give us new terms. First, for us, R is going to be either regular local ring or standard graded polynomial over a field K. M is going to be the most important, well, either here the maximal ideal or here the maximal homogeneous ideal. And then K, well, in this one is just R over M, and in this one is just this field. We're going to take I contained in the radical. And this is because we're going to play with symbolic powers. And then we're going to take the symbolic Riesz algebra, which I'm going to denote this way. Which we know that is not always finally generated. And the associated gradient of the symbolic Riesz algebra, which is this one. And then an observation, we were working with the ordinary Riesz algebra. This one will be, if we forget about the symbolic part, this one is this one, modulo this one times I. But here, because symbolic Riesz algebra may not be finally generated, that this is not going to work. So, but this is still a question of that one, just like that is a bit more complicated. So if J is equal to the sum of I m plus 1 times 2n, this is an ideal here. So then the associated gradient, the symbolic associated gradient of R is the Riesz algebra, this is symbolic Riesz algebra, modulo this ideal J. Also, an observation is that this has as a direct summand R over I. No? This here, this split self, no? Because this, by definition, is okay. Now I'm gonna go here. Definition. This is work with the definition in the work with Alessandro Stefani, Jonathan Montagno, and myself. We say that I contained in R is symbolic Q if there exists a splitting, a map from R1 over P to R and splitting such that P of I symbolic, this is going to be weird, but it's going to make sense, the exponents, in a moment. MP plus 1 over P, is contained in I symbolic M plus 1. Okay. So let me justify this, and then I'm gonna do something here. So first is this one, okay. I m plus 1 p, this one, 1 over p. That one is contained in I m p plus 1. No? Just because this number is smaller than this one. Okay? So if I apply phi to this one, or phi to this one, well, this is going to be contained in I m plus 1. And I forgot to say this happens for every n in n. Okay? So we have that. Okay. What happens here? Okay. So if we want to do this, look at this map. If we want to push this to the Riesz algebra, this will have degree n plus 1 times p over p. The degree of this one is n plus 1. And the degree of this one is n plus 1. So this is going to help me to define a graded map with the Riesz gradient in the symbolic Riesz algebra. So with this one, I can define a map that goes from R, I, the result, the Riesz ring, to the symbolic Riesz ring. And this is going to be defined. This is going to be defined by, in something homogeneous, RT A over P. This is going to be equal to P of R if P divides A, and this makes sense for what's happening here, or 0 otherwise. Okay? But then, a first question is, Luis, why do you use P for symbolic purity, this contained here, and you went all the way to work with this? That seems too much. And it's because I want this map to induce a map in the state gradient. So since phi of I symbolic MP plus 1 over P is contained in I n plus 1, we're going to have that Psi of J is contained in J. So this map descends to the accelerated gradient. So we have an induced map to the accelerated gradient, which is the quotient of this one by this. Sorry, 1 over P. The gradient of P symbolic R, 1 over P, the gradient I symbolic R. And because phi wasn't splitting, all of these are going to be splittings. So, corollary or theorem if I is symbolically pure, then but the symbolic Riesz algebra and the celebrated are the pure. Something I have to be careful here is, for everything that we have done with the purity, we're assuming Noetherian and finite. This still works if we work only with the purity, or purity is going to be, I guess, F split. And even if these are not finally generated, it still makes sense. However, if this turns out to be Noetherian, then we know that with purity we can bound regularities, we can bind A invariants. So we combine the regularity, so we will be able to bound the degrees of the generators of the final equations. So this is like an application of purity to the symbolic Gauss algebras. If they are not n, which it does not always happen, but sometimes for nice families of ideas, it happens. For instance, if I is a square free monomial ideal, this happens. Oh, I never did this. Sorry. It's gonna be a moment. Okay, I fixed it. Okay. Proposition. I'm gonna do this. This is a feather types criterion. Suppose that I is a radical, no, sorry. The following are equivalent. First, I is symbolic pure. So now we can translate the statement about the splitting, sending something to something into a column-like statement as we do with feathers. So I mp plus 1 symbolic is to the power of p, column with I, the intersection over every n. This is not contained in m bracket p. Okay. Because here we need a bunch of splittings in every single degree. And then this seems too hard to test because we have an infinite intersection here. But it can be done.
Is it column I?
Oh no, thank you. Column I symbolic n plus 1. Thank you. And then this one is enough to go to until the big height of y, which is now a finite condition that can be tested in the computer if the computer is either too powerful or we are too lucky. And then another proposition is that I h p minus 1 is contained if h is equal to the big height of I is contained in this intersection. This is a different one. So here, you can guess one of the theorems, no? So this is telling us if, for Larry, if I h p minus 1 is not contained in m bracket p, then I is symbolic pure. And luckily, we just met an ideal that satisfies this property, the ideal of t by t minors. So the ideal of t by t minors of a generic matrix is symbolically pure. So this is the last one, and it's just go back to the terminal of this. Okay. So the same one that we have, the x is a matrix of variables, the ideal I is the ideal of maximum, of t by t minors, and that stuff. So, well, let me first mention a theorem by Bruns and Conca. But the symbolic Gauss algebra. Here S, remember S was the polynomial ring with variables in the matrix. And the associated gradient. This one. Noetherian, finally generated. And then the theorem, again with Alessandro and Jonathan, is the symbolic Gris algebra of the T by T minus and the associated derivative of the T by T minus. These are strongly regular. This is not only a pure, they are strongly regular. And because this is finally generated, we can bound the degrees of the defining equations if you write this as a polynomial ring quotient with something. I'm not going to prove this because the proof we already did it. It's the same proof that we did to prove Hofstadter affinity theorem for determinant rings. Take the polynomial. We know that this thing is satisfied, the polynomial that we built. Then take a variable that the same variable goes to 1, that splitting. That splitting, the field that we works with the T that we define for the symbolic. You localize, and then the things became 1 by induction. Pretty much, it's not the same proof, but it's very, very close to it. So I'm not going to prove it because we pretty much did it. There are some corollaries. So the limit of the regularity of R over I symbolic, S over I symbolic N, this exists. So this over N, a limit when it goes to infinity. To mention in characteristic 0, Claudio Raicu did a formula for this in many, many cases using representation theory. So this is the first comment. In prime characteristic, because we know that these are noetherian, we know that the regularity is going to be a quasi-linear function. So the linear part, the coefficient of the linear part may vary. We have finite, but it may vary. So the way this proof works is proving that all of those coefficients are actually the same. However, the constant term may vary still. So this implies that the regularity is, you have like a few linear functions, and then depending on certain congruous classes, you have a linear functions. So that means that the constant term and the slope and the constant term may vary. What we prove is that all the slopes are the same. But there are cases, well, maybe not here, but in symbolic pure rings, where the constants still vary, even though the slopes are the same. So this exists, and you want to work in this problem, we suspect, but we don't know, that the limit is T. The same as in characteristic 0, by the work of Claudio Raicu. Second, this is first. Second, the depth of the symbolic powers, this stabilizes. Again, there is a point where it's eventually constant, and we know this one we know at what? At t squared minus 1. And then proving this, we can recover the following corollary from Bruns and Conker. We can show that if we take the x diagonal order, the one as before, then the initial powers of this, the initial idea of the symbolic powers is the same as the first initial idea, which turns out to be square free, or the initial. And what happens is we use a purity to prove that the Riesz algebra given by this is reduced. So using a version of the theorem that we discussed by Unity, Siemens, and Vasconcelos, we get the quality. And these ideas of symbolic purity or purity, they work. I mean, we just discussed them for determinant ideas, but for instance, it worked also for monomial ideas. And then one can recover a lot of results that have been done before, but in with a characteristic P flavor proof. And then this also works for matrices, square symmetric matrices. Not all the theorems, but a lot of the theorems that we discussed for genetic also works. You take an antisymmetric matrix and then take the packets instead of the minors. Then the same things work. If you care about clinical matrices, then a lot of this stuff also works. So this is a versatile way to get characteristic P stuff results in symbolic ideas and symbolic algebras. I think this is a good moment to finish in the appendix for 10 minutes.